Hello everyone, and welcome back to Reverse Engineering Linux 32-bit Applications. In this video, we're going to continue our discussion of stack buffer overflows. In particular, we're going to talk a little bit more about some of the built-in protections for Linux. By now, you should be getting the idea that it's actually kind of hard to do a stack buffer overflow in Linux. It's almost like there's a worldwide community that's been working to try to prevent this problem for a really long time. So unlike the situation with 32-bit Windows, this is a lot more complicated. So kind of picking up from our discussion last time, we had talked about this problem where I ran my little test script and we said, what's going on here is that this location keeps changing on me. So we said, oh, I'm just going to say, go to the stack and execute off of the stack. Well, that didn't work so well because the location of the stack kept changing. And then we said, all right, well, I'm going to jump to an instruction. And that instruction is located in a library. And then we noticed that that location is also a variable. It's not the same every time I run my program. We said, okay, what can we do? Now, when we looked at our memory regions, we noticed that every time this region for loading in my libc changed. What didn't change was this. My application itself is always located at the same address. So if I got lucky, I could say, all right, can I find this value, FFE4, jump to stack pointer somewhere on my stack? And the answer was no, I couldn't. And at least not for my simple application. Maybe if I had a longer application, I could get lucky, and that might be the case. Now, something we didn't talk about before is this. I look at my different locations, and I notice that here is my stack. My stack goes from here, FFC3C000 to FFC5D000. So that is the location of my stack. Notice the permissions. I do not have the ability to execute things on the stack anyway. So this is a challenge. This is something I would have to fix. Now, in order to get this to work, I would have to rebuild my program and what am I going to give it as a parameter? So I gave it the no stack protector, and now I can give it an additional parameter, and my additional parameter is going to be -z followed by exec stack. So let me give it that. -z exec stack. It's rebuilt my application. I'm going to rerun my little script. And let's see if it's any different. I'll view my memory regions. And sure enough, now my stack is executable. So I've solved one of my problems. But I haven't solved all of my problems. And you'll notice that my stack moved. So that was another problem. The stack is not in a consistent location. The libraries are not loaded in a consistent location. Is there any way that I can change this? Well, this behavior is behavior from the operating system. This is not behavior that comes from the compiler. So what can I do here? Well, let me go back to my shell for a second. So I'll go ahead and close this. I'm going to go to my shell, and I'm going to go ahead and give myself a root shell. And now I want to look at proc sys kernel and see what's in there. And I will notice there is this guy, randomize VA space. So this guy will in fact randomize my virtual address space. And if I cat what's in there now, it says 2. That's the value that's in there. Now here's what I can do. I can echo 0 to this location. Should probably have my greater than sign. To proc sys kernel randomize VA space. And now let's see what happens if I decide to rerun this. It's 0. I'm going to log out as root, and just to verify, I'm going to cat this. And it's still 0. So this behavior has been disabled. Rerun my script. And now I will look at my stack space. Look at my different memory regions. I see my stack space is now, this time, at FF, FD, D000. And what about my libc? Libc is now at F7, FD, A000. Just for interest's sake, I'm going to close this app. I'm going to rerun it. And I'm going to view this again. And sure enough, what do I have here? I have my stack being loaded at FF, FD, D000, the exact same place. This is loaded at F7, FD, A000. So I'm good to go now. So now what can I do? I'm going to go ahead and rerun this application now that these randomized addresses have been disabled. So I'll go ahead and run it to my first breakpoint. I'll go ahead and do my analysis. Set my second breakpoint in the usual place. run to that. And now I'm going to step over, step, and now here I am at leave. So here is the return address that I've overwritten, but it has the wrong value. I should be pointing here, 6A42, etc. Let me go back to my script for a second and verify that. 6A42, etc. Where does that start? It starts at FFFFCF50. So I can write down that new location, FFFCF50. That is the new place. And let me go ahead and enter that. So it's 50. CF. FF. FF. Let me save that. Exit. Rerun my script. Run to my first checkpoint. Run my analyzer. Set my second breakpoint and just go ahead and run to that. Step, 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 step. Here's my leave. And what do we have? FFFFCF50. So yes, in fact, I have finally figured out how to get it to jump to my shellcode that I've placed here on the stack. Now, I had to do several things, and we're not there yet because there's still a chance that this will not run on the exact version of Linux that I am running at the time. So, we'll see if we get lucky and if this brings up a shell for me or not. It might not. But it'll be an interesting little experiment. Regardless of whether or not I collected, or rather I should say selected, the correct shellcode, we had to go through a lot of hoops in order to get here. So let's go ahead and jump. And so now here we are. And this is our shellcode. If I went back to my browser where I downloaded this shellcode, I would see that this is in fact the correct shellcode. So let me go ahead and step through this. And it said, hey, I'm unhappy. So the shellcode that I selected was not compatible with my version of Linux that I'm running here. But, we were pretty close. So that's one way. What's another way? We could do the jump ESP. So now that we've gotten rid of that randomization of our virtual address space, and we've made the stack executable. So we had to somehow recompile the application to get rid of this protection, right? So first of all, we had the stack protector. We compiled that away. Then we had the non-executable stack. We compiled that away as well. Then we went out to the operating system and we disabled this randomization feature in the operating system. So we had to do quite a bit just to exploit a simple buffer overflow here in Linux. And you might get a little bit of a hint as to why exploit developers. Why are they exploiting Windows? Well, number one, there are more Windows systems out there that are being run by people who you possibly want to exploit. And it's a lot easier to exploit Windows systems. So let's go ahead and have a look back here at our shell code. So that was not working so well for us. I mean, again, we could select another bit of shell code. Here's an interesting bit of shell code. It's going to read the password file, and it's going to send the contents to a certain address. We might try that one. And this one will read the password file as well. And here is that new shellcode. So let me go ahead and try to use this. I'll go ahead and modify my script. And I'll put this in as my new shellcode. So, save it. And we'll run it again. All right, I'm just going to go ahead and let it run. And it says, hey, this executed and it ended normally with 0 as its output. So in this case, I was able to run my program and I was able to pass it some shellcode and nothing bad happened. But it did, in fact, read my password file, or at least I think that it did, but it says it's going to read this file. And what's it going to do with it? It doesn't say it's going to do anything with it. So that is that shellcode. Now, there was another shellcode here that said, I'm going to read it, and I am going to, in fact, print it out. So I'm going to print it out to a certain port. So we could go ahead and try this one. And it even tells me, how do I get my file? I run netcat as a listener on this address. And here is my shellcode. Let me copy that. Go back to my script. Paste it. Like so. And let's run it again. And before we run it, let's remind ourselves what we were supposed to do. Run this command, netcat. Let me go ahead and start that in another window. So I'm listening. Let's see if I can successfully exploit. And it's unhappy with me because I have an unterminated quoted string. So again, you can run into some complications because of the fact that some of these characters will be doing weird things in your terminal. Let's just see if we can get away with this. And, honestly, we can't. The problem that we're running into here is that one of these bytes in here is going to show up as a quote of some sort. And that's going to cause our problem that we're getting right here. So, how do you get around that? Now, we'll talk about some of those more advanced techniques later in this course, but there are ways to get around that. So one of the ways to get around this is to encode your cell code. This is something you might be familiar with if, for example, you've used Metasploit before. And you can use different encoders and you can say, these are the bad characters. Pretty much everybody doesn't like a null character. And that can cause trouble. But you can also have other characters, such as a quote, that will cause trouble. Okay, so what did we learn in this video? We learned a couple of things. If you are somehow lucky enough to find an application that has been compiled without turning off the stack execution protection, without having the stack protector, and without having random locations that things are loaded into memory, and if you're really lucky, you just might be able to exploit a stack buffer overflow on Linux. So what if all those things aren't true? Well, then you can try to exploit it anyway. So we'll talk about those more advanced techniques in some future videos. But that's all that I had for this video. As a reminder, this is one in the family of videos here at Pentester Academy. Everything you ever wanted to know about information security is available here. And I hope to see you in this class or another class soon. So we will see you then.